Does anyone have any questions about lectures, tutorials, or the final project, which is due in more or less 1 week? No questions? Not, we can start. We can continue last week's lecture. So today, last week we couldn't cover hypothesis testing as I tried to. So we will cover it today. Last week we did the central limit theorem and confidence intervals. Okay. Today it's hypothesis testing, then we're going to talk about types of errors in hypothesis testing. And then different types of tests, one or two tailed tests, hypothesis testing with small sample size, t-distribution, and then a comparison of two samples. The last step, which is useful also for your tutorials. So I've already uploaded your tutorial questions for next week, last tutorial. Okay. So, before we start, let me correct. Last week I talked about the central limit theorem, and then I gave you an example, which was this one, and asked you to answer it. And the issue was that I set a sample of 6 cats. And I told you that the central limit theorem is for samples above, equal or above 30. Okay? So I corrected the example. So the solution is still the same, A. Okay? But I corrected the numbers in the example so that, the sample size is above 30, so you can apply the central limit theorem. Okay? And so the slides from last week have been corrected. Okay? And now have this, but the solution is still A, which is the average is the same as the population, 250 milliliters. The standard error of the distribution of the samples is the standard error of the population divided by square root of sample size. Okay? Square root of n. So square root of 36 is 6. 3 divided by 6 is the half. That's the answer. Okay, so I just wanted to correct it from last week. Okay? All good? So the answer is A. Okay. So let's start with hypothesis testing. The idea is like this. We want to make statements about the population parameter on the basis of sample evidence. Okay, so here the parameter that we're going to talk about is going to be the average. Okay, we're only going to talk about the average. Your textbook also has another one more distribution, the chi-square distribution. You can use that to make inference about the standard deviation. Okay? But I'm not going to talk about that. Okay? So here we're only going to talk about averages. Okay? And the idea is like this. There is a true population distribution. So suppose type of people or students in this lecture hall. Okay? There is a distribution of student types. Okay? I don't know the exact distribution of student types, but I might make some suppositions, some hypotheses, something that I think is true. Okay? I might say, I think that the average student type here is 1.7 meters. Okay? And then what I would do is take a sample of students, suppose 10 students, measure the average height of this sample, the 10 students, get the standard deviation in the sample, and then I would use that to check if the sample, the population, so the student height in this classroom is 1.7 meters. Okay? The way it's actually done, I will explain in a few minutes, okay? So, the question is a yes or no question. And so either the sample results support or not the hypothesis. Okay, so either the information that you got from the sample is consistent with your assumptions about the population or not. Okay? Oops. Wrong button. Okay. Hypothesis tests are conducted at the significance level. So remember when we talked about confidence intervals? We talked about the 90% confidence interval, the 95% confidence interval, the 99%, 99% confidence interval. Here, similar idea, we're going to talk about significance level. Basically the rest of the distribution that we're not using. And we're going to talk about 10%, 5%, or 1%. Okay? Again, why these numbers? The idea of these numbers is, well, it's historical. So we've used these numbers. The first person who set this up set these numbers. But there's another particular issue. When you do hypothesis testing, okay, you get a yes or no answer. Okay? But it's something like this. The yes answer is actually not very clear. The yes answer says the sample is consistent with the population, with my assumptions about the population. So the sample of students' height is consistent with 1.7 meters for the entire for the whole class here. Okay? That doesn't say that the average height of the students is actually 1.7. Okay? So it just says that it is consistent. So it could be 1.7. We don't know if it is or not, but it could be. So being consistent is not particularly useful. The yes answer, which is going to be the do not reject answer, is not particularly useful. The only useful answers that you can get from statistics are no answers. Those are very useful. And what they say is, I do a sample, so suppose I reject my hypothesis. So the average height in my sample is very different, significantly different from my assumption about the population, 1.7. So then, what I'm saying is, when I reject, the statement is it's so unlikely that when I take a random sample from the population, that I will get a sample with, let's say, 1.80. So unlikely that if it comes from this population that I think of, so unlikely that I'll get this sample average, that I have to say that it is probably that my assumptions about the population are incorrect. Okay? So then I have to say I'm making the wrong assumption about the population. Because it's extremely unlikely that these results come out from this population. So that's why it has to be the significance level has to be very small. 10%, 5%, or 1%. Because if I made it bigger, okay, so here, when I have, suppose, a significance level of 5%, it means 5 in 100 samples will give me a height of students that is different from 1.7. Only 5 in 100 samples. So if I take a sample and I get a height which is different from 1.7, I'll think, well, it's so unlikely for it to be true that maybe my assumptions about the height of students' height in this class is wrong. Okay? Now, this is extremely essential to understanding hypothesis testing. Okay? The statements that you want, the statements that are really relevant, are the negative statements. So that's going to affect how you set up your hypothesis. Okay? Because the positive statements, meaning, oh yes, the sample is consistent with the population, they don't tell you much. They say, well, it might be that it is 1.7 meters high. It is consistent, but it doesn't say that it actually is 1.7. Okay? Well, but if you say it's not 1.70, that's a much stronger argument. It's so unlikely that if I draw a random sample from a normal distribution with this parameter, that I will get a sample that's so different from 1.70 that I have to think that maybe my assumptions about the normal distribution, about the parameter, are wrong. Okay? And that's inference. Inference is understanding from the sample what is happening, what is true in the population. Right? The yes statement doesn't tell you what's happening in the population. It could be 1.70 is consistent, but it could also be something else. The no statement tells you something about the population. I know that at least it's not 1.7. Okay? So that's more information than I had before. So that's very important. Okay? This will become, I hope it will become clearer when I do a one-sided, one-tailed hypothesis test. Okay? In that section, when we set up the assumptions, you'll see that why we have to set the assumptions like that. Questions about it? So, when we set up the hypothesis, we always set up simultaneously two hypotheses. One that we assume is true, and one which we think is false. So the hypothesis that we think is true is the null hypothesis. And that's going to be the hypothesis that's going to be tested. Okay? The alternative hypothesis is basically it's called the logical negation of the first hypothesis. So whatever is not true in the null hypothesis is in the alternative hypothesis. Okay, so one thing, you always set up the null hypothesis where the equal sign, so you set up, okay, average is equal to a certain amount, or average is smaller or equal to a certain, or larger is equal to a certain amount. So the equal sign is always in the null hypothesis. Okay? That's always true. Even in some books, when they do a one-sided test, the null hypothesis doesn't have an inequality sign, which is what you would use for a one-tailed test. It only has an equal sign. Some textbooks. Okay? Okay. So these are the steps to do the hypothesis testing. First, you define your hypothesis, what you think is happening in the population. Okay? Some value to some parameter. You take the sample from the population, and you test the sample to see if it supports the hypothesis. If the hypothesis is highly improbable, then you reject it. Otherwise, do not reject it. So, some books say accept the null hypothesis. Accept is not the best term. Okay? Because the only thing that we can say from hypothesis testing is that if we do not reject, is that the population parameter, the population average, could be what's stated in the null hypothesis. Okay? We're not saying that it is. You cannot make that statement from hypothesis testing. Okay? Only that it could be. Okay? So, again, highly improbable. The more improbable, the smaller the significance level, the higher the status for improbability, meaning that it's so unlikely. So I'll show you that in a second. Questions about this? Everybody good? Okay. So, how do we do the hypothesis testing? Suppose that you set the level. So the first thing that you set is what are the hypotheses being tested. So suppose that we're looking for the average of the population, and we're saying that it's equal to a certain number, and we set the alternative hypothesis that it is different from a certain number. Okay? And that is the numbers we're thinking about. Okay? Then the second part is you set the level of significance. Okay? And the level of significance is going to determine these probabilities in the wings. Okay? In the tails of the distribution. And so basically, if it falls, so you want to check that it is between these numbers. Suppose that you said it comes from a normal distribution. You don't know exactly what are the numbers here from the normal distribution, but you do know from the standard normal distribution. Okay? So in the standard normal distribution, the value of z such that the probability that it's smaller or equal to 0.025 is minus 1.96, and the probability that z is greater or equal to 1.96 is 0.025. Okay? If the value that you get from your sample size, when you standardize it, falls between these two numbers, then you do not reject the null hypothesis. If it falls outside these numbers, then you reject the null hypothesis. Okay? So, again, if it falls outside these numbers, the likelihood that it came from this distribution is so small, 5%, right? Because the probability that it is Z smaller squiggle is so small that you have to say it's so unlikely that maybe my assumption about the null hypothesis, H0, is not true. Okay? Hopefully this will become a little bit clearer when we start with the examples. We have plenty of examples in the slides. I need to skip actually a few so that we cover it. Okay. So procedure to test, to do hypothesis testing. Start with stating the hypothesis. Average equals to a certain amount. A certain value. And alternative hypothesis as well, average different from this number. Okay? Assume that the null hypothesis is true. And then see if the sample confirms that assumption or not. State the significance level. Okay? State basically the values, the probability that it is either smaller or larger, both of them. So these significance levels are the sum of these two probabilities. Okay? One question. So what happens to, remember that I said last week that there was a relationship between hypothesis testing and confidence intervals. Right? That they are similar in some way. If you remember, we used this number to build the 95% confidence interval. This was part of the construction of the confidence interval. And actually, if we were to look at, in this distribution, this is the confidence interval. Okay? This is basically a confidence interval. If I increase the significance level from 5 to 10%, what's going to happen to the confidence interval? So there's two options. Increase or shrink. So who says increase? Who says shrink? Okay. Shrink. So if you increase the probabilities here on each side, that's going to shrink your confidence interval. So how is that going to affect your hypothesis testing? Remember, the statements that you want to say is, my sample is so unlikely that my sample comes from this distribution that I reject the null hypothesis. So do you think it's more likely or less likely to reject the null hypothesis if I shrink that interval, if I increase the area where the sample can come from and reject the null hypothesis? So do you think it's more likely to reject the null hypothesis who thinks less likely? So it is more likely. Okay? So that means that the statements you want to say, which is, oh, it's so improbable that I would reject the null hypothesis, it's a weaker statement. Because it's more likely that I will reject the null hypothesis. It is more likely that they will fall within these areas, the tails of the distribution, if I increase that. Okay? So the smaller the significance level, let's say the more, it's probably not exactly the correct term, but let's say the more certain you are about the statement. And if you put the significance level that says 50%, then the hypothesis testing makes no sense, because there's a 50-50 chance that you will reject it. So you won't say that, oh, this sample is so unlikely that you came from this distribution that I would question my assumptions about the population. Questions about this? Yeah. It seems like a very small detail, but it is important. Okay? And it's basically the essence of hypothesis testing. So let's go back to the procedure. State your hypothesis, select your significance level, and then based on the significance level, you're going to find from the standard normal distribution what are the cutoff values. Okay? And so if it is 10%, then the cutoff values will be between minus 1.65 and plus 1.65, 5% 1.962, plus minus 1.962, plus 1.96, and 1% minus 2.58 to plus 2.58. Okay? Then you calculate test statistics. So remember, you are comparing to, you're going to use the standard normal distribution to make the comparison, right? So you know what is the distribution of the sample from the central limit theorem, right? So if you calculate this number is a standardized number that comes from the standard normal distribution. So it's something that you can compare against the standard normal distribution. Because in the average, if you subtract the mean of the sample average, which is the population, so the sample average should be equal to the one from the population, right? So subtract the mean, divide by the standard error, okay? From the sample standard error is the standard deviation of the population divided by the square root of the sample size, okay? This value will have a standard normal distribution for which you can compare the critical values from hypothesis test, that you got before. Okay? So this is your test statistic. So then you compare the test statistic with the critical values. It is within the critical values. Come to a conclusion. Basically, do you reject the null hypothesis or do not reject the null hypothesis? And then put your conclusion into it. That's it. So what does that say about the population? Okay? Questions about this? If there are no questions, let's practice. So maybe let me read the question. Store manager believes that the average amount spent on jam and marmalade is £1.50. A random sample of 80 shoppers was selected from a large population and tested about the amount spent per week on these items. The results from the survey showed that the amount spent per week in these areas was £1.40 with a standard deviation of 0.15. Does this lend to support the manager's opinion at the 5% significance level? Okay. So how would you do the hypothesis testing? First, state the hypothesis, the null hypothesis. What does the manager believe is true? What does the manager believe is true? That the average is 1.50, right? Then you need to pick the significance level. You need to know the significance level. What is the significance level here? 5%. And then construct the test statistic. Okay? And what information do you need for the test statistic? Average from the sample, which is 1.40. Average of the population, subtract the average of the population. Minus 1.50 divided by standard deviation in the population, 0.15, divided itself by square root of sample size. What is sample size? 8. And then you compare that to the critical values that you get from the standard normal distribution. Okay? So, let me show you how. Let me write this down. Oops, no, there you go. Okay, so can everybody see this? Yeah? Okay. Step 1, state the hypothesis. Okay. And the hypothesis is the average amount that customers spend in the store on jam and marmalade is equal to £1.50. What will be the alternative hypothesis that you need also to state? You need to state both of them. So what is the alternative hypothesis? It's basically different. So again, the alternative hypothesis is basically the logical negation of the null hypothesis. Okay? So step 1 is done. Step 2, state the significance level. Okay, and that's given in our in the question right now as 5%. Okay. So what does this 5% mean? In the standard normal distribution, okay, the probability here and the probability here, and this is, let's call them Z1, Z2, each tail has half of the 5%. Okay? Each tail has 2.5%. 2.5%. And then what you do is state the critical values. Okay? And the critical values are basically this Z1 and Z2. Okay? So what you're looking for is from the standard normal distribution, the probability that it is Z smaller or equal to Z1 is 2.5%, and the probability that it is greater or equal to Z2 is 2.5%. Remember, the distribution is symmetric, so they're going to be, one is a negative number, the other is going to be the positive number. Okay, because the distribution is symmetric. So these numbers, you usually just memorize them. So, because it's just, you're going to use them so often that you end up memorizing them. Okay, this Z1 is minus 1.96. This Z2 plus 1.96. Okay? I'm going to shift this up a little bit. Maybe not so much. Okay. Okay. So now, calculate the test statistic. Okay? From the central limit theorem, you know that the averages, the sample mean, has a normal distribution. The test statistic, what you need to do is standardize that sample mean. Basically make it from the normal distribution to a standard normal distribution. That's what the test statistic is. So you can compare it with these critical values from the standard normal distribution. Okay? So step 4 is basically calculate test statistic. And that's basically, you'll get a z-score if you find x bar minus mu minus the average, sigma square root of n. Okay? And the reason why we have this test statistic is because x bar follows a normal distribution with average mu and standard error okay? And so what do we know from the question? We know that x bar is equal to 1.40, sigma 0.15, n equals to 80, right? And the other thing that we know that we're going to use, the other information we're going to use is the null hypothesis. We're going to assume that it is true and use that here. Okay, so we're going to assume mu is equal to 1.3 because that's the hypothesis that we were testing. Okay? So you can calculate that number and you're going to get, next page, Z is equal to 1.4 minus 1.5 divided by 0.15 divided by square root of 80, and that's basically minus 0.1 divided by 0.0167, and that is minus 5.96. Okay? And then, after this, step 5 compare the test statistic with the critical values. Okay. Step 5. So, the critical values that we had, minus 1.96 plus 1.96, that doesn't look very, but it's basically like this, right? So, where does it fall in the distribution? In the center, to the left of minus 1.96, or to the right of plus 1.96? It falls to the left, right? 5.96. Okay. So the next step, which is come to a conclusion. So in which area does it fall? What do you do with this? So you have two options. It's a yes or no, right? So reject or do not reject. So based on this, who says reject? Very good. Who says do not reject? No. Reject, okay? Because it falls in this area. Whenever it falls in this area, you reject. So step 6, come to a conclusion, and that is reject A0. Reject the null hypothesis at the 5% significance level. Okay? Step 7 is write this, put this into words. Okay? So, has everybody finished copying? So that I can switch back to the slides. So the question was, the store manager believes that the average amount spent on jam and marmalade is £1.50 for the customers that come in. So what does the sample say? It says basically that based on this sample, it is unlikely that customers that come into the store are spending £1.50. Okay? Actually, it seems like they're spending an amount smaller than that. Questions about this? So now I'm going to skip example 2 because I'm not going to have time to do all the examples that I put it up. put that on the slide. So, and let's just look at example 3. Okay. So the Central Tax Office says that the average income in Port Elizabeth is $15,000. A sample of 45 people found that their mean income to be $14,300. The standard deviation of 2,000. Use a 5% significance level to check claims. What is the effect of using a 1% significance level? Okay. So, what is the null hypothesis here? What do you want to check? Average income is 15,000. What information does the sample give you? It basically gives you average in the sample was 14,300 and the standard deviation of that sample was 2,000. The sample size is 45. Okay, so this is the information from here. And we want to check if this sample is consistent with a population with an average of 15,000. Average income of 15,000. Okay, at the 5% and 1% significance level. So, let's do that. Okay. Step 1, state your hypothesis. What is the hypothesis? Null hypothesis, what you believe to be true is that the average income is 15,000. What is the alternative hypothesis that you also must state always is that it's not 15,000. Okay? Step 2, select the significance level. Okay? And this is given in the question. We're asked for 2 significance levels, 5% and 1%. At the 5%, you have on each side, on each tail, the probability is 2.5%. Okay? And if you have a significance level of 1%, then basically what we're looking at is 0.5% on each tail. Step 3 is state the critical values. So, for the first one, it's the same as before. We're looking for a number, well, 2 numbers. we're not looking for number z, so that probability is 2.5%. I just said in the previous that this number that you're looking for is 1.96. So the critical values here, 1.96, minus 1.96 and 1.96. Okay? And then for the other one, what we're looking for is a number in the standard normal distribution, so that the probability that it is smaller or equal to that number is 0.5%, and the probability that it is greater or equal to that number is 0.5%. Greater or equal to that number is 0.5%, and that is 2.58. Minus 2.58, 2.58. Okay? Everybody good? Yes? Okay. Step 4, calculate the test statistic. You know that the sample average has a normal distribution with mean mu and standard error sigma divided by square root of n. So to compare the distribution of the sample average, I need to standardize it to the standard normal distribution, calculate the z-score so that I can make the comparison. Okay, so what I do is step 4, calculate the test statistic. Okay. And that is basically the sample average that we had was 14,300, and the average, the null hypothesis, was 15,000. The standard deviation in the sample was 2,000. The sample size was 45. Okay, so that number is going to be minus 700 divided by 298.4 minus 2.35. Step 5 is compare this test statistic to the critical values that we had before. So the test statistic is minus 2.35. Where does that fall here? Left, middle, or right? Who says left? Who says middle? Who says right? Left. Okay? So minus 2.35. here, where does it fall? Left, center, middle. Who says left? Who says center? Good. Who says right? No one? Good. So what you're going to do when you compare the test statistic with the critical values for when the significance level is 5%, minus 2.35 is smaller than minus 1.96. When it is 1%, minus 2.58, minus 2.35, 2.58. So when the significance level is 5%, it is to the left of the critical value. When it is 1%, it is between the critical values. Okay? And then step 6 is come to a conclusion. What is the conclusion for the 5% significance level? For the 5% significance level, what is the conclusion, please? Who thinks reject? Okay. Good. Who thinks do not reject? Okay, good. Reject. Bless you. For the 1%, what do you do? Reject. Who thinks it's reject? Who thinks it's do not reject? There you go. Okay? So the reason why I wanted to do this particular exercise is to, can you see here why I'm saying that the smaller the significance level, the more demanding the test is. Right? When you have a 5% significance level, you reject the null hypothesis. So you make a statement which is, it's so unlikely, only 5 in 100 samples would give me a sample average which is so different from my assumed population average that I have to question if the population average is correct. Okay? So I have to reject my null hypothesis about the population average. When you make it more demanding, 1%, you're saying only 1 in 100 samples. Okay? And it does not pass that test, meaning you do not reject. And in the end, what you're saying with the 1% is, well, the sample could come from this population average. Okay? But the only meaningful from a population with this population average. The only meaningful statements, though, in hypothesis testing is it's so unlikely that this sample average comes from a population with average mu that I have to question my assumptions about the population average. So if I increase the standard, which is basically lower the significance level, I end up making a lot the less meaningful statement, which is, yes, it could have come from that population. Are people following? Any questions about this? Before we go to the break, let me just talk about types of error. Okay. So when we do hypothesis testing, there are two types of errors that you can make, sort of obvious, which is type 1, you reject the null hypothesis when the null hypothesis is true, so you're making the wrong decision. And the type 2 is the other wrong decision. The null hypothesis, you do not reject the null hypothesis when the null hypothesis is false. So the first one says that sample actually came from that population, and I made a mistake. Okay? And I said that it didn't. The second says that sample did not come from that population, and I said that it did. Okay? So this type 1 error is actually also the significance level, alpha. That is, this will be the probability of making a type 1 error. And the type 2 error is also usually called beta. Okay? Beta. And there's a relationship between the two. So, okay, this is the table stating exactly what I said. Suppose that it is the population, it is true, and you do not reject, this is the correct decision. If you reject, you do a type 2 error. Suppose that it is true, and you do reject, then you do a type 1 error. And if it was actually false, you do correct decision. Right? So the relationship between the two are like this. Here the known distribution is the distribution from the sample. Here the unknown distribution is the distribution from the population. Suppose that it looks like this. Okay? When you set the significance level, you're saying that for this distribution that comes from the sample, if it sort of falls here, you reject the null hypothesis. But if the true distribution was like that, your error, your type 2 error is going to be this error. Okay? Which is that, again, we're saying if it falls below the significance level, the cutoff from the significance level that you set, right, you do not reject from the sample population, right? But notice that the true population average is different from the sample population. And so all this area is basically when you do not reject, but in fact you should have rejected because the population average was different. Population average was different from the sample average. Okay? So this would be alpha, type 1 error, this would be beta. And you cannot basically put both to 0. If you increase one, if you sort of decrease one type of error, you're going to increase the other. So usually what people do is set the significance level and then try to minimize the type 2 error. And one way to minimize the type 2 error is to increase the sample size. The bigger the sample size, your standard deviation is going to decrease, and the least likely that you get this type 2 error. about this? Okay, this is important to know. Okay, so let's have a break. Let's come back at 3:15, 7 minutes break, and we'll talk about quantitative tests.
In this example, you didn't give us the significance level.
So I need to talk about that, which is that when I don't give you the significance level, usually what people will use is the 5%. So you assume 5%. If not given, 5%. Okay? Forgot that was example. Okay. Hello. Oh, okay. Can I do that at the end of the lecture? So I can think?
Yeah.
At the end of the lecture, okay? So that I can think clearly about this, because right now I'm thinking about hypothesis testing. Okay?
Examples after the subpoint.
Yes.
Which one?
As many as possible.
Yes. So maybe about binomial distribution, we should add an example of it.
Yeah.
And the connectiveness is about the example of company.
Yes. No, hopefully you can use also either another company example or the same company. Another example from the same company.
Should we use the framework like this? We just abstract the framework in one picture and then we add some more explanation on the other slide.
That's fine. Okay.
About question, can we use the company A and then we relate it to the company B? That's
Sure, that's okay. Yeah.
About the data, should we use the data from the news or we can make it by ourselves?
Up to you. You can make it by yourself.
Okay.
Doesn't matter. It's up to you. Okay? Yeah. No, it's either. It's okay.
It's okay.
Yeah.
And we can just write down on the paper that picture.
Yes, but good quality picture.
Good quality picture. Okay.
Bad quality picture I cannot read.
Okay.
Okay?
That's fine.
Yeah, that's fine.
Okay, thank you.
Yeah.
This question, it didn't get the significance level,
So when it's not stated, it is 5%. Okay. So suppose that this is the true distribution, okay, of mu. True distribution with mu, right? This is sample distribution, right? And so you sort of you standardize it, right? And then you set the significance level, and then you make this is do not reject, and here you do reject. Okay? Right? So is the true mu different from the sample average? Is the true average different from the sample average? Yes or no? Yes, it is, right? So here, what type of error? Well, this would be type 1. This here. Okay? What are you doing here with the sample, with your test statistic? Do not reject. But the true one is actually different. So you're doing, this is the type 2 error, the beta.
So the right one is the population distribution?
Yeah, exactly. So that you don't, well, we don't know, right? Okay.
Can we use the microscope to
You can do, it's okay. I don't put any limit on what you can do. Many limits on what you can do. Okay.
Okay. Let's get back because we still have lots to cover and not much time. Okay. So now we're looking at different, you know, the basic hypothesis testing, different types of tests. Okay. So far, what we've done is called the two-tailed test, where the null hypothesis is basically say equal to some value or different from another value, from a certain value. Okay? And basically, if it falls on either one of the tails, you reject the null hypothesis. Okay, so that's why it's called two-tailed test. But you can also might be interested in basically you might be interested, for instance, on just one type of fact. So you might be interested on, suppose here the example, if you are a consumer and you buy a bar of chocolate or some bottled drink, your own concern that the weight or the contents is not smaller than what's safe. If it is more, no problem, right? If you buy a 1 liter bottle, but they give you 1.5 liters, that's not a problem. Okay? For the producer, it's exactly the opposite. If they want to make sure that they're not spending too much in the production, so they want to make sure that they're not putting into the bottles more than 1 liter of water. Okay? So different people might be interested in different hypotheses, different things, right? And so you might just want to be interested on the one-tailed test, where you look at the average, population average is smaller or equal to some value, and the alternative that is greater, or hypothesis test that the population average is greater or equal to some value, and the alternative is smaller. Okay? Remember, the equal sign always goes with the null hypothesis. Okay? To the point where some books, they will state this with just an equal sign. Rather than small or equal, just put equal sign. Okay? And so what happens is, instead of dividing the probability of getting a value into the two tails, you put everything into one tail. Okay? So this would be the null hypothesis, the probability that it is smaller or equal to something. So you assume that any value below is okay. If it is larger, it is a problem. Okay? Any value of the population average which is smaller is fine. Anything that's too large is a problem, and I should reject. And I set this cutoff at the cutoff, the critical value is 1.65. The significance level is 5%, so that this probability under the distribution is 5% on one side of it. Okay, and you can do the same for 1%, the same thing. The probability is smaller, and you can do it to the other side. So if you have an average greater or equal to a certain value, any sample values that are large is not a problem, but if they are too small, then it's a problem, and I'll have to check. Okay? So this is the difference between two-tailed tests and one-tailed tests. You just put all the probability to one side, into one-tailed test. Okay. Let's do one or two examples, maybe just one, from the two-sided test. Oh, sorry, let me actually read to you the question. Let's do this one. Example 3. Book check mail, order, charge customers a flat rate for delivery based on mean weight of packages of 1.75 kilograms, and you think that the standard deviation should be the population of half a kilogram. Postage costs are risen, it is likely that the mean weight is greater than 1.75 kilograms. The company checked around a sample of 100 packages and found a mean weight of 1.86. So, does that support the view that the mean weight is more than 1.75 kilograms? Okay? So remember the steps for hypothesis testing. Okay? First, state the hypothesis. That's this one. Yeah. So in this case, what would be the null hypothesis? Average weight greater than 1.75, greater or equal to 1.75, or average weight smaller or equal to 1.75. So who thinks the first one is the true hypothesis? Greater or equal to 1.75. Null hypothesis. The answer is smaller or equal to 1.75. Okay? Remember, the only meaningful statements are those where I reject the null hypothesis. So if I want to check that it is, if I'm afraid that it will be larger than 1.75, what I check if it is smaller. Is it smaller or equal to 1.75? Because if it is smaller, no problem. It's only problem if it is too big. So if I reject the null hypothesis, if I get the sample average which is too big, then it is a problem. Okay? So again, it's all because the meaningful statements are the ones in which I reject. What I don't want is values which have weight packages that weigh more than 1.75. Okay? And I'm fine if they weigh less. So I'm going to start by assuming that they weigh less. If I find a sample which is the average weight is so big, to 175, then I can be sure, or I'll say that it's so unlikely that it came from a sample with a weight smaller or equal to 1.75, that I have to assume that the average weight is larger than 1.75. Okay? It's a complicated statement, but it's all about what I said at the beginning. The only meaningful statements are the ones in which you reject the null hypothesis. So this is first point. And then the second point is state the significance level. What is the significance level which is asked in the question? The issue is it doesn't say. So not all your questions will state what is the significance level. And if you don't state, people pick 5%. Okay, so if there's no indication of a significance level, pick 5%. Okay? Okay, so let me write down, these are the 2 points that I wanted to mention before starting. So let me write it down now. Oops, wrong button. Yeah. Okay. So, as I was saying, step 1, state the hypothesis. Okay. The null hypothesis is average smaller or equal to 1.75. Okay. Because if it is smaller or equal to 1.75, it's not a problem. It's only a problem if it is bigger. And the only meaningful statements are those where I reject the null hypothesis. So if I reject that it is smaller, then I think it might be bigger. The population, the true population average is bigger. And that is a problem. And that's what I wanted to check. Okay? The alternative is the logical negation of the null hypothesis, meaning all the other values greater than 1.75. State the significance level. Step 2, and that is 5%, and because it is assumed, because it's not stated in the question, when it's not stated, assume 5%. Then state the critical values. Step 3.
Okay. So I have a distribution, standard normal distribution here. What I want to check is if the sample average is not too big, right? So here I'm going to put the cutoff to the right, and this probability in the tail, it's going to be one tail, it's going to be 5%. Okay? Instead of dividing by the 2, just all on one side. And if you look up this from a standard normal distribution, which is the probability that z greater or equal to z1 is equal to 0.05, that's going to give you a value of 1.65. Okay? That's the critical values. Step 4, yes, calculate the test statistic. So what you do is, again, sample mean has a normal distribution with average mu, standard deviation sigma divided by square root of n. You can standardize this distribution to a z-score and then compare it with the critical values. Right? So the test statistic is basically subtract the average and divide by the standard error. We're given in the question that the sample average was 1.86. Your null hypothesis, that's why you need the equal sign in the null hypothesis, is that it is equal to 1.75. That's the value you're going to use, even on the one-sided test. Okay? 1.75. Okay? And you're going to divide that by 0.5 square root of 100. And that's going to give you a number of 0.11 divided by 0.05. That is 2.2. Step 5, compare your test statistic to the critical values. So here, where does it fall? Your test statistic. 2.2, where does it fall here? To the left or to the right? Who thinks to the right? That is the right answer. Very good. So here, 2.2. Step 6, come to a conclusion. So what is the conclusion? So if it falls in this area, what do you say? Do not reject. Yes. And if it falls in this area, what do you say? Reject. So what is the conclusion here? Reject. Okay? Why did we reject? the sample average was so different from what we thought was the population average that it's so unlikely that the population average is actually 1.75 or less. Okay? Therefore, it is unlikely that it came from that population average. It is unlikely that the population average is true. Okay? And then step 7 is put your conclusion into English. So the evidence from the sample does not support the view that the mean weight of packages is 1.75 kilograms. Instead, it supports the alternative hypothesis that the mean weight is more than 1.75 kilograms. So we can say, when we reject, we can say that it is more than 1.75. If we do not reject, we could say, well, it is consistent with being less than 1.75, but we don't know. Okay? We don't know exactly how much it is. Questions about this? Running out of time quickly. No questions? All the other examples for this are similar, so I'm going to skip those. I'm going to skip also example 4. They're all the same thing, just go through the steps, all very similar. And I'm going to look at the t-distribution. Okay? Again, another type of test. So the t-distribution is similar to the normal distribution in the sense that it is symmetrical, it is for continuous variable, and it is bell-shaped. The difference is that it is flatter and more elongated. And it is the right distribution to use when you do hypothesis testing with the sample size less than 30. Okay? So, when you have a small sample size, instead of comparing values from a normal distribution, you compare values from a t-distribution. Okay? So, to look up the values on the t-distribution, you basically need two things, which is one, the critical value, the probability that is more or equal to, and then something which is the degrees of freedom, which we talked about before. Remember, if we use the standard, that was a small issue in terms of the textbook, which is not consistent with other textbooks. The correction, if you use the sample standard deviation versus the population standard deviation. If you use the sample standard deviation, you divide it by square root of degrees of freedom, n minus 1. And this is exactly what we need to use here for the t-distribution. The degrees of freedom, n minus 1. Okay? So, n minus 1. The sample size minus 1. So, here is a standard normal distribution. And this is the t-distribution for a sample size of 2. So 1 degree of freedom. And this would be a t-distribution for a sample size of 11, which is a t-distribution, so degrees of freedom of 10. Right? And as the sample size increases, it gets more and more similar to the standard normal distribution. So if you have a big sample size, you can just use the standard normal. Okay? That's why the cutoff is at 30. Questions about this? Okay, so how to look up the values? The tables are for one cell only. Okay, suppose that we are doing
5% significance. This is a two-sided test for significance level, so two-sided test. Suppose we have a two-sided test, so the sample size is 3. Significance level 5%, and you want to calculate the test, the critical values. You want to find the critical values. Which comes from the P statistics table. So what we're looking is for two-sided, each side, the two-sided test, so the probability on each side is 2.5%. So T 0.025, comma, degrees of freedom, sample size of 3, so 3 minus 1, 2. Okay? So this is basically the table for the t-distribution. What we're looking for is the probability 2.5 with a degree of freedom of 2. This number, 4.3027. This section of equal column, this column in this row, 4.3027. Okay? So the usual way of looking about it. So the only difference is, well, that the test statistic is going to have a t-distribution rather than a standard normal distribution. Okay, so that's going to change, well, not going to change exactly the test statistic, but it's going to change which values you compare. Okay? Now, examples. Again, I have way too many examples, then I have time. So I'm just going to pick one of them. And I'll probably pick the last one. Okay. So let me do example 4 from the t-distribution. The supermarket is getting complaints that its tins of strawberries contain a lot of juice, but not enough strawberries. The team from the supermarket makes a supervised visit to the supplier who is about to deliver a batch. Each tin in this batch is claimed to have a minimum of 30 grams of fruit, but the random sample of 15 tins found only 287 grams, with a standard deviation of 80 grams. What conclusion can the supermarket make? Okay? So the first question is, step 1 is state the hypothesis. What is the problem here? That is less than 300. So the only meaningful statement is where you reject the null hypothesis. So what will be your null hypothesis? That the average is greater or equal to 300 grams. Right? So that's going to be your null hypothesis. The second part is significance level. What is the significance level in the question? Not stated. So they don't say what significance level they want. So what do? Pick 5%. Okay? Where are you going to then the critical values? From which distribution are you going to get the critical values? Standard normal or t-distribution? T-distribution. Right? Because the sample size is smaller than 30, 15. Okay? So you're going to look up a value on the t-distribution, which is 0.05, comma, degrees of freedom 14, 15 minus 1. Okay?
So these are the three things which are particularly different in this test of hypothesis. So let me write it down, everything, slowly. Don't do that. So, step 1, set up the hypothesis. Again, here the case is you're worried that it is too small, the quantity, right? So let's assume that it is big, and if we reject that, then we know that it is small. So let's assume that on average, each can has 300 grams or more of strawberries. Okay? Let's assume that. And so, again, remember, the equal sign goes with the null hypothesis. The alternative is that the average is smaller than 300 grams. Always take the null hypothesis and the alternative hypothesis, both of them together. Step 2, state the critical values. Sorry, the significance level. Step 2, state the significance level. Okay? And that is, it's not stated in the question, so we're going to assume 5%. Okay? Because that's standard. Then state the critical values. Step 3, state the critical values. So sample size n is equal to 15, which implies, so it's smaller than 30, it implies a t distribution. So you're going to look up it's a one-sided test, right? If the values are greater than a certain amount, that's fine. So there's a cutoff here, and this area has a probability of 5%. And you're going to look up in the t distribution a value t1, so that the probability that x smaller or equal to t1 is equal to 0.05. The t distribution that's on your textbook is only for x greater or equal to a certain number. But the issue is that the t distribution is symmetric, so you can use probability that x greater or equal to t2. Or actually, sorry, minus t1. So it has the opposite side. Okay? 0 minus t1, where t1 is negative. Okay? And if you look this up in the tables, which value? So we need to define, the other thing is that sample size is 15, which means the degrees of freedom V n minus 1 is equal to 14. So you look up this value in a t distribution, 0.05, 14. And that's going to be, the value in the table is going to be 1.761. But this is, you are looking for the negative value. So minus, and so this is equal to minus 1.761. Okay? This is the only hard part, which is finding out the critical values, slightly different from before. You need to know the sample size, you get the, and then look it up in the tables. Okay? Next, step 4, calculate the test statistic. And the test statistic now, when you standardize it, because the sample size is small, doesn't have a standard normal distribution, but a t distribution. So let's say t, a value in the t distribution, can be found x bar minus mu sigma square root of n, same as before. And this is basically 287, that's what you found in the sample average. Your null hypothesis, what you care about if it is greater or equal to 300. Your standard error is 18, and your sample size is square root of 15. Okay? Now there's, well, never mind, I will not mention something more confused. 15. Okay? So you're going to get minus 13 divided by 4.81. This 4.81 is wrong, but it's close enough, okay? I use square root of 14 for another reason which we're not going to get into. So you need to just check again, but you're going to get the same conclusion, don't worry. And so that's going to be minus 2.703. Okay? Again, the number, if you correct the calculations, I used the wrong number there, it's going to be slightly different. Okay? But it's not going to change the question. So, step 5 is compare your test statistic to the critical values. Right? So you have here the distribution, what we're looking for. What happens if it is to the right of minus 1.761? What do you do? Well, okay. And so actually let's start with another question. Minus 2.703 is to the left or to the right of minus 1.761. Is it here, this value? Is it here or here? So left, everybody? Yes. Very good. So it should be somewhere, yeah, minus 2.703. And then step 6 is come to a conclusion. If you are to the right of minus 1.761, what should be your conclusion? Do not reject. Right? Actually, this continues and on and on. Anyway. Okay? If you are to the left of minus 1.765, what is your conclusion? Reject. So in this case, because it is to the left of minus 1.761, you reject another hypothesis. Reject H0. So what is the statement? So step 7, put into English. What does this say? This is saying, it is so unlikely that when you take the sample, you're going to get an average of 287 grams, that you have to question if it comes from a population where the average weight in the can is 300 grams or more. So it is unlikely that the population has, so that the average weight in the cans is 300 grams or more. Okay? Because it is very unlikely that if it has 300 grams or more, you'll get a sample with 287 grams. Okay? Questions about this? Before we go, just one more last type of test, okay? And then this test is in your tutorials, the last type of test. And it's just only 2 slides, okay? And it is comparison of 2 means. So sometimes you don't want just to know, is it equal? Is the population small or equal? The average in the population small or equal to a certain amount? You might want to ask, do these 2 samples come from the same population? Okay? And that means basically checking if the samples, averages, the means, are too different or not. Okay? So what you do, what's different here is that you're saying, okay, the population average from the first mean is equal to the population average of the second mean. Or the difference in population averages is 0. From which you drew 2 samples. That's not, I've uploaded recently, well, just today, these slides, okay? But they are now online. You can check them afterwards. So the difference is equal to 0, or the difference is different from 0. Then you significance level the same way. If it is a big sample, look into standard normal distribution. If it is a small sample, get your critical values from the t-distribution. And then you calculate the test statistic, which is just the difference in averages minus what your hypothesis is about the difference in average, which is 0. And divided by the big difference is here, the standard error, which is the variance of the first sample divided by the sample size, the first sample size, plus the variance of the second sample divided by the second sample size of the second sample. That is the only difference. Okay, which is just one more formula. And then you compare the test statistics to the critical values, you come to a conclusion, and you put it into it. Okay? And to practice this, you have some questions in the tutorial, okay, that require you to use this formula. Okay? Questions about this? If not, I've run out of time. And
Yeah. Pay attention to this question here about the tests. If you use a non-random bias sample, how would you use that? Okay? See you guys. Tutorials, there are tutorials next week. And if I don't see you in tutorials, see you guys next on Friday. For the last one. Thank you, Simon. Mm-hmm.